Okay. So perhaps we should start.
Mhm.
Okay. All right. Okay. Hello, everyone. Welcome. Welcome to this series of One World Signal Processing seminars. And today we're very glad to have Professor Gesualdo Scutari from Purdue University to give us a talk on his recent works. So let me first introduce the speaker, and then we'll briefly talk about, mention about the rules, the procedures, and then we'll start. Okay. So Professor Scutari receives the PhD degree from electrical engineering from University of Rome in 2005. He is currently the Thomas and Jane Schmidt Rising Star Associate Professor from School of Industrial Engineering, Purdue University. His research interests include continuous and distributed optimization, equilibrium programming, and their applications in signal processing and machine learning. So he has done many impactful work in these areas, from some early works of analyzing multi-user word of feeling algorithms, which I learned about in my PhD studies, and to the most recent works about distributed optimization that we're going to hear today. So Dr. Scutari currently is a senior area editor for EEE transaction and signal processing, and also an associate editor for Cyan Journal on Optimization. So among many awards he has received a NSF Career Award and also a Signal Processing Society Young Author Best Paper Award, and many other conference paper awards. We just learned this week he has recently been elevated to IEEE Fellow. Congratulations, Gesualdo. Today he's going to discuss his most recent work about distributed optimization and statistical learning. Okay, so now before we start, let me briefly mention that for the audience, if you have questions, please text in the chat. So we'll have people monitoring the chat, and there also will be, if the questions can be answered quickly, we will answer them, or we will sort of collect those and ask Aldo at the very end. Okay, all right. Aldo, the Zoom floor is all yours. Thank you very much for joining us today. Please.
Okay, thanks, Mingy, for the nice introduction and nice words, and also thanks to all the organizers. I mean, first of all, to invite me, it's an honor to be one of the speakers, and also for the great service that you're doing to the community in this moment. I mean, it's good that at least we have the chance to meet virtually. And yeah, today, as the title says, I will talk about basically some of my thoughts. I will share with you some thoughts about the interplay between distributed optimization and statistics, given the growing interest in applying distributed optimization in machine learning. And some of the results that I'm going to present are still preliminary, but I hope that they will give you the sense, will support the entire take-home message of the talk, which is that we need more statistical thinking in distributed optimization. Okay, so this work would have not been possible without my collaborators, starting from my student Amir, my postdoc Marie, Gilbert postdoc fellow, and Ying Sun, who will join Penn State Electrical Engineering in January as assistant professor. And let me also mention that this idea of this interplay between statistics and distributed optimization was triggered by an initiative, seed funding initiative inside my school, the Purdue Industrial Engineering, and this was wanted by our department head. Okay, so let's start with the motivation. Our goal is to learn, make prediction and decision from networking data, and data that are distributed across different nodes of the network. Think of applications like sensor network or edge computing, or just multi-core machines, where basically we want to split maybe the data across different machines or clusters because we want to speed up the computation and also cope with the storage issue and so on. And in this talk in particular, I will focus on computational architecture of this type, where basically there is no centralized node handling or coordinating the optimization, but basically all the nodes are at the same level, and they can just talk to each other and get the information that they need. Just to clarify a bit the terminology, for the rest of the talk, whenever I will talk about algorithms implementable on this kind of architecture with no centralized or no master node, I will talk about distributed algorithms. In contrast with the algorithms that can run on star topologies where there is a master node controlling the optimization, in this case, I will refer to them as centralized algorithms because this is an architecture with a centralized node. Okay. So in this distributed setting, the big challenge is to perform our analytics without moving the data to a single place. And when it comes to design our distributed algorithms, I would say that the main desiderata can be summarized roughly in these items. On one hand, we want fast algorithm, but don't forget that our goal is perform our analytics. So we want also to have good statistical performance, like generalization error or any other form of statistical error. And on top of that, these algorithms are running on distributed system. And communication efficiency is another important component. Actually, I would say that if you look at many benchmarks, the bottleneck in many cases is given by the communication. Only 10% of the entire time is CPU time. The rest is mainly communication. So this is clearly an important component. And on top of that, of course, this scheme are large scale, and it's quite difficult to have a single clock. So we want a synchronous modus operandi, and we want, of course, resilience against network failure and so on. Of course, when it comes to design to meet these desiderata, clearly there are trade-offs that we need to make. Trade-off in terms of statistical error, in terms of computation and communications. For example, what are the statistical guarantees that we can achieve given a finite computation budget and for example, given a finite computation and communication budget? And our understanding of such trade-offs in the distributed setting is very limited. We know, don't read me wrong, I mean, we know a lot about distributed optimization, distributed algorithm, but from a pure optimization point of view. We know how fast they are, we know how fast they can be, so lower bounds, and we know also how to accelerate that. But this is only half of the story. These results have only indirect implications on the trade-off that I'm mentioning here, because they lack completely the statistical component. And on the other hand, there are statistical computational trade-off in the centralized setting. But again, only half of the story. They lack of the network component. And the network component introduces another dimension and with new challenges and also new potentials. And for example, can we achieve centralized statistical guarantees when data are distributed? At which communication cost? Or what is the scalability of our performance in terms of number of samples, dimensions, and so on? So all these are basically to address these grand challenges. I believe that we need to rethink a bit our approach and combine at a more fundamental level these three ingredients: the statistical component, the computational part, and including the networking component. And in particular, I claim that we need to bring more statistical thinking in the current distributed optimization. And this is the entire take-home message of the talk. In order to convince you that our knowledge is to convince you about our non-understanding, I'll tell you two stories. The first story is on the design side, and it deals with a classical low-dimensional setting. We have a lot of data with respect to the unknowns, and I'll show you that if we inject the statistical thinking into distributed optimization, we can design more efficient algorithm from a communication perspective than what statistically oblivious current schemes are. And the second vignette is on the analysis in the high dimensional setting, in the typical setting of big data, where the number of unknowns is comparable or even larger than basically the number of samples. And in this case, I will give you examples showing that if we use that example showing that existing theory of distributed optimization breaks dramatically when it comes to predict the behavior of existing algorithms in the high dimensional set. Some algorithms work much better than what the theory predicts, and some others do not work at all, and we don't understand why. So let me spend the next 10 minutes at fairly high level to elaborate on these two vignettes, and then I'll try to address some of the issues coming out of this brief explanation. Okay, the first vignette. The first vignette is basically, let's consider a very standard problem. We want to estimate a parameter theta star, solution of a stochastic optimization problem. Let's assume the loss function convex, and P is the distribution of the data. We don't know the distribution P, so what we do in practice is to, instead of attacking directly this problem, we construct the sample average approximation of this stochastic loss, averaging the loss L over n observation, drawn from the distribution P. And given that this function, this problem is not strongly convex, we add a regularizer here to make the problem easier from a computational point of view, and also to serve, and this also serves, this regularizer also serves for generalization purposes. And if you want, as a concrete example, just to not be so abstract, you can consider a linear regression problem where the unknown parameter is linearly related to the data y and xi, our observation, and we are using a quadratic loss. But this is just an example. You can consider many more general learning tasks. The key point here is that these data, these n samples, are not centrally available, but are distributed across m machines in a network. So we split this data n in across n machine, and each machine will get n samples only. And if I then rewrite this loss function across the agents, splitting these samples across the n machine, I just need to take the average of the loss over the n machines, and each of the terms here represents the loss of one agent, average over the data owned by that agent. Okay, very simple partition here. And our interest here is, okay, now this problem is basically a so-called learnable problem under fairly general assumption, meaning that if we choose properly the regularizer, in particular of this order, remember m times n is the total number of samples, then what we know is that the population loss in the empirical minimizer will converge to the optimal population loss at this rate, 1 over square root of the total number of samples. And this is, and I use this notation to hide the dependence of the dimension d, because we are in the low dimensional setting. So I'm assuming that d is fixed, n is the number of samples is what can grow. And okay, and this is on the statistical, what we know from a statistical point of view. But what can we do computationally? At the end of the day, we need to compute theta hat. From a computational point of view, if you look at this problem, this is a textbook strongly convex problem with strongly convexity L, and also let's assume that all the nice assumptions that we need to claim that the gradient is also L Lipschitz continuous. And so if you look at the literature of existing distributed algorithms, you will see that there are algorithms that basically will give you linear convergence with the number of communications of this order, where I'm hiding the dependence on the network, but I'm just highlighting the dependence on the optimization parameter, which is this polynomial with this kappa g, which is basically the condition number of my problem. The ratio between the Lipschitz constants and the strongly convexity constant. And basically, if you substitute now the specific expression that you get from the regularizer, you will see that this condition number will scale with the square root of the total number of samples. In other words, if you look at the total number of communications, what we see here is that the total number of communications will grow with the local sample size. And this is a kind of undesirable result, because it shows a kind of a dilemma between statistical accuracy and communications. Basically, if I have more local samples, and I can improve my estimation, but I have to pay in terms of communications, which is quite of counterintuitive if you think about that, because the more samples I have locally, the closer, the more data and more information I have. How can it be that I need to communicate more? And this result is a consequence of the fact that the existing distributed optimization method that basically enjoy this rate are basically statistically oblivious. They are designed for arbitrary local functions Fi, and they do not account for the fact that there is more structure in the problem. This local function Fi are basically the average of data from the same distribution of the same loss. It's clearly that they are related to each other. And in fact, from a statistical point of view, this is captured by a property that is called statistical similarity. Under fairly general assumption, you can check these papers. Basically, what happens is that each local function Fi gets closer and closer to the average empirical loss when the local sample size grows. And this happens at this rate. And this similarity is measured in terms of Hessians. And these coefficients, keep in mind this symbol beta, we measure basically how similar are the functions. So the question now is that, can we use this statistical similarity and inject this and have a statistical informed design in terms of optimization? We can do that, and actually we need to go beyond gradient schemes, and this has been done in the centralized case. And basically the schemes that we need is the mirror descent. If you instead of minimizing the gradient or a first order approximation of the loss, you define a function that basically contains basically the data, the local loss of the master, and the master is then will solve this optimization problem after getting the average gradient, after building the gradient, the average gradient, getting the local gradient from basically the local nodes. You will basically, this scheme has the property that if you look at the convergence rate, the number of communications that I need to reach an epsilon solution is now independent of the local sample size, which makes more sense. And by the way, there are also schemes in the literature, still on star topology, that look at the problem from a different angle. But if you use this umbrella of mirror descent, you can see that they are roughly mirror descent schemes. Just as a curiosity, because otherwise this may sound a bit mysterious, why the mirror descent? For those of you, this is just a technical parenthesis, but for those of you who are familiar with mirror descent, the reason why, you may have noticed that in the moment that you inject you want to use the statistical similarity property into the optimization design, you will notice that the loss function, the empirical loss, is not only L strongly convex, lambda strongly convex, and L smooth, but it's so-called relatively strongly convex with respect to the function phi with these coefficients, and relatively smooth with respect to the function phi with coefficient 1. Why is this important? Because if you define a relative condition number like the ratio of this one times this, you will see that this relative condition number is independent on the number of local samples. And this is now the mirror descent. It's a scheme that achieves linear rate exactly with this condition number. That's the reason why mirror descent will give me this rate independent on the local sample size. Now the question is that, how can we employ statistical similarity into the distributed optimization design over network, given that now agents no longer have access to there is no master node, and then, so this is the first question. But before answering the question, let's move to the second vignette, which in my opinion is even more interesting, because this second vignette is basically is an example of high dimensional statistics over network. We are now in a setting where the dimension D is no longer fixed, but is basically of even larger than the total sample size. And we are in a regime where both D and N can grow, and basically along with other parameters like the sparsity and so on. Just to be concrete, let's consider a problem that is known to the community, an estimation of a sparse vector from linear measurements, and each node here in the network owns a branch of these measurements. And the goal is to estimate this parameter theta star, solving a constraint lasso problem over a network, where now each agent owns just a branch of data. And we are in this regime, okay, as in this regime where D and N are both large. And again, let's compare statistics and computation. From a statistical point of view, again, this problem is learnable because under the assumptions that I will describe later, we can control the statistical error, so the distance between what we can compute and what we want. And this statistical error goes of, the order of the statistical error is this, which means that even if we are in a regime where D and N are growing, with D faster than N, meaning that D divided by N can grow, as long as N, I don't know if I have the formula here, no, as long as N goes like S log D, the model becomes more and more complicated, so D grows, but I have enough samples, at least this order, I can control this ratio and the statistical error, and I can obtain statistically consistent estimate. Now, the question is, what happens to the computation in this case? So how fast can I compute? And more importantly, how does my computation scale, the rate scale with the dimension and the samples in this regime, where basically I can still make statistically consistent estimates? Well, let's look from a computational point of view what we are dealing with. We have a standard optimization problem, and this problem is now no longer strongly convex, because if you look at the Hessian of the data matrix, this is a matrix of dimension D times N, and given in sum of rank N rank 1 matrices, which means that these matrices cannot be full rank, the Hessian cannot be full rank, so there are some directions where this function is flat. And more importantly, another important component that affects the convergence speed of an optimization algorithm is the Lipschitz constant. If you look at the Lipschitz constant, which in this case is the largest eigenvalue of the Hessian, with the high probability, if you consider a random matrix here, the order is D divided by N, which means that, remember, we are in a regime where D divided by N can grow. So which means that the Lipschitz constant is growing in this regime. So if you use these two information and you just apply the existing theory of distributed algorithms, that's what we can conclude. We can conclude that because of the lack of strongly convexity, we can achieve sublinear rate. And given that in this regime of interest where the statistical error is constant, so we can achieve good estimate, the algorithm will slow down. So in order to compute this good estimate, the algorithm will require more and more communications. And it's not even clear in this context how the role of the network in the scalability. So this is what we know from the existing theory. Now, let's test how good these predictions are running some experiment. And I keep here the conclusion that we get from the theory. Okay, the first experiment is basically, we just test one of the widely known and famous algorithm, the distributed gradient algorithm, introduced in the paper of Sayed for least squares and in these seminal papers, and then in a more general setting, the paper of Angeli and Edic and Asu. And basically what I do here is to plot the estimation error, so the distance of the iterates from the ground truth that we want to compute, and versus the iterations. And for different values of the step size, and basically each curve refers to a different step size. The lower the floor, the smaller the step size. And the black line that you see over here is basically the statistical error, the best we can hope for. Okay, and as you can see here, we can observe there are two comments here. The first comment is that, as you can see, these curves are showing linear rate. And if we tune properly the step size, this rate matches the statistical error. And this is in contradiction with what this says, sublinear rate. The second observation that we can make here is that, however, in order to achieve low estimation errors, we need to reduce the step size, which means that we need to slow down the algorithm. See the rate, the slope is going to change. So there is a speed accuracy dilemma, even in the high dimensional case. This is known even in the low dimension. But this is for a given number of samples and dimension. Let's look now at the scalability. Remember, we are in this regime where if the model becomes more complicated, but we have enough samples, we can still perform statistical accurate estimate. What happens to the computation in this case? What we plot here is the estimation error versus the iteration, and each curve refers to a different dimension for the problem. The dimensions are growing in this direction, and whenever we increase the dimension, we also scale properly. We also add the samples properly according to what the statistical theory is suggesting. As you can see, in the centralized case, the centralized algorithm the rate of the centralized algorithm is fairly invariant. This is the number of iterations to reach, the estimation error versus the number of iterations. So the centralized projection gradient is fairly invariant, which is exactly what we would like to have, right? If you have a problem that if the statistical error is not changing, I would like to be to keep the same convergence rate, even if the problem the dimension grows and the samples grow as well. For DGD, the story is different. If you put in the linear scale, in a different scale, you can see clearly this is the same picture just for DGD. You see that you are losing, you don't have scalability that you want. When the model becomes more complicated, even if you can preserve the same statistical error, you are losing on the rate. So you are slowing down your algorithm. Okay. And okay, but then if this is just an issue of DGD, or I mean, what about the other algorithms? There are many other algorithms beyond DGD. And if you go check in the literature and simulate a few other algorithms, of course, this is not an exhaustive list. We have an example, for example, here, what we simulated some of them. You see the list over here. And the situation is even less clear, more confusing. Some algorithms, first of all of them are converging linearly, which still contradicts what the theory says over here. But the situation is more complicated because different algorithms have different behaviors. For example, look, this algorithm here, Sonata, seems to be rate invariant, which basically breaks this second conclusion over here. And other algorithms seems to scale do not have a good scaling. For example, this is from or they seems to have a decent scaling for some dimensions, and then when you change the dimension, they are breaking. I mean, it really depends on the situation. So as you can see, there is a lot of confusion. So the take-home message of all this story is that basically the existing theory of distributed optimization is not adequate to predict the statistical optimization properties in the high dimensional setting. And this is because this theory lacks completely of the statistical component. So now I hope that I gave you, I convinced you that we need to basically merge at a more fundamental level statistical thinking and optimization. And now we can go a bit more into the details and try to basically answer some of these questions. The first part, so let me first start with the low dimensional setting and see how to enforce statistical preconditioning in the distributed optimization. So I will introduce first an algorithm that is known. So I apologize, some of you already know the algorithm, but we can build on this scheme for our purposes. So the setting is the standard setting that I introduced already before as a special case. So we have M machines. on a network, and every node has a function, an objective function to minimize, and we are interested in minimizing the average of these functions. And we can also have an extra these functions are differentiable and smooth, and basically the extra function here may not be differentiable, and we can use this function to enforce regularization or even constraints if this is an extended value function. So this problem is clearly cannot be solved at the level of each agent, because each agent knows only its own function. So the standard fairly known approach at this point is to introduce local copies controlled by each agent. Agent I owns the variable theta I, which is an estimate of theta, and the idea is that all these agents in parallel will update this variable theta in a two-step. First, they solve an optimization problem that locally is a kind of an approximation of the centralized problem. I will get back to this in a minute. And then once they introduce this intermediate variable, they broadcast this to their neighbors. And then the second step is to generate the new point, the update, just doing a convex combination of the intermediate variable of the neighbors or of their neighbors. So, and this is what every agent does. Okay. Now, let's look quickly at the structure of the optimization problem that each agent is going to solve. We need to approximate the sum function here. So the structure, the optimization problem, the objective function at the level of each agent, so it looks like this. There is one term that is an approximation. You can interpret this FI like an approximation of the function of that agent. For example, you can think of a first order approximation, or you can think of a second order approximation, or you can think of the function itself. I will go back to this in a minute to show a few examples. The second term here basically plays the role of an approximation of the gradient of the function of the other agents. This is an information that locally I don't have, so I try to estimate the gradient of the other functions to correct the direction of the optimization for agent I. And the way to approximate the gradient of the others is through this term that basically this G variable that plays the role of the estimate of the total gradient. It's like the master node, what the master node does. And then I subtract the gradient of the agent, because the gradient of agent I, it's already in the local function. And then this GI is updated iteratively using only local information in order to estimate this gradient. I will not go into detail. This is a well-known idea known as gradient tracking, and it's basically, this can be done through a dynamic consensus scheme. It's not important at this point. It's now an idea that is widely used in the literature. So, but let's see instead what's the impact on the convergence of the choice of the surrogate functions. So the standard, the fairly natural idea is to use as function fi the first order approximation. And so you just use this function. If you use this function under the standard assumptions that the smooth part is strongly convex, and this is the global condition number. And this parameter rho captures the connectivity of the network, so is the second largest eigenvalue of the weight matrix. And the smaller, the faster the network, roughly speaking, aggregates information. And then remember the parameter beta that I introduced at a certain point in the vignette 1 when I was talking about the statistical similarity between the local functions and the average loss. So keeping in mind all of this, if you use the surrogate, what you can show is that if the network is sufficiently good, and or if you are on a star topology, the rate you can reach an epsilon solution in this number of communications, which is pretty much the same performance of the centralized gradient algorithm. And the threshold on the network is kind of, as expected, depends on how bad is the or good is the optimization problem. The more difficult the problem, the larger the kappa G, the smaller rho has to be. I didn't show here the detail, but if you look at the paper, you can find a more refined analysis of this rate. When this condition is not satisfied, this dependence will deteriorate and becomes quadratic. So you slow down your algorithm if the network is not sufficiently fast. You can still recover linear dependence on the condition number if you use multiple rounds of communications per iteration, employing some form of acceleration. In particular, this is done with Chebyshev acceleration polynomial. And basically you can see that the communication still, if you neglect log factor, is still of the order of kappa g, and with an extra slowdown coming from the network. But it doesn't matter. This is a detail. What the important thing here is that if you look at this rate and you apply this result to the first problem that I showed you, the vignette one, the condition number will depend on the local sample size. So the message is that if you use only first order information locally, this is the take-home message of this part, you don't get any benefit from the statistical similarity. The number of communications will grow with the local sample size, which is something that we don't like. So to put a remedy of this, we need to use, if you want to mimic the mirror descent, you need to use different surrogate functions. And in particular, for example, if you use as a surrogate functions your local loss plus a proximal term, what we can show that in this case, again, if the network is sufficiently good, the number of communications that you need to reach an epsilon solution is now independent on the condition number and depends on this ratio, where beta measures exactly the similarity of the statistical similarity of your function. In other words, in the setting of the vignette one that I showed you before, this beta divided by mu is roughly independent on the local sample size. It's just the square root of the number of machines. If you are not on a star or the network is not that good, again, you can use the Chebyshev acceleration to keep a good dependence on the this statistical similarity, and basically that's the rate that you get. But this is not important. The take-home message of the second part is that we can save communication injecting employing local preconditioning via surrogate functions. And now, of course, this beta, if the functions are not similar, like beta can be even larger than the Lipschitz constant. So which means that when there is no statistical similarity on the table, this quantity can be larger than the condition number, which means that the overall argument can perform worse when there is no similarity. This makes sense, right? If the local functions are completely different, why should I want to minimize something retaining my own, weighting more my own information? And this is something we also observe numerically, because this is an example where we show the number of iterations that you need to reach an epsilon solution of 10 to minus 7 as a function of beta divided by mu. And as you can see, this is what you get when you do linearization, and this is what you get when you employ a statistical precondition. As you can see, as long as beta divided by mu, this is a simulation, this is original regression. As long as beta divided by mu is roughly better than the condition number, of course, you have an advantage in employing this form of local statistical preconditioning. Otherwise, it's better that you just linearize. Okay, just one comment is, of course, this does not come for free. We are saving communications, but technically we are supposed to solve an optimization problem that looks like this, where now you need to minimize your own local function plus a linear term. In many cases, you don't have a closed form solution for this problem. And which means that this can be computationally expensive, and the rate that I showed you before refers only to communication rounds, but does not account the computational part. And so in order to alleviate this issue, we can, of course, what we can do is, instead of minimizing just exactly your own function, you can consider a second order approximation of your local function plus a cubic regularization. And the rest remains the same. And you can show that this problem can be cast into a min-max quadratic program in D+1 variable. And if you can tolerate matrix inversion, you can reduce this to a scalar maximization program, univariate maximization program. Okay. And basically the interesting result is that if you use now this other surrogate and you look at the performance, how does this affect the overall rate? Well, communication wise, the rate is not going to change. In the strongly convex case, you can still use the up to the second order information and take advantage of this, of the faster rate coming from this statistical similarity. Let me also mention, because I think it's interesting, the case where the function is not strongly convex, but it's only convex, the total loss, because there's an interesting interplay between statistical precision and speed, convergence speed. In this case, if the function is just convex, we can show that in order to reach an epsilon solution on the objective value, we need this number of communications if the precisions that I'm targeting is larger than beta squared. If I want smaller precision, then the rate will slow down. This is square time faster than this. So basically, this is 1 over t squared, this is 1 over t, roughly. Okay. So this is interesting because this will tell us now that the interplay between optimization and statistics. Because from an optimization point of view, you can target any accuracy. But from a statistical point of view, given that our target is not solving the optimization problem, but actually estimating the parameter of the population coming from the minimization of the population, in a fairly general setting, the statistical precision that we target is roughly of this order. If you substitute the number inside, you will see that given that beta is of this order, when you substitute the expression, you will see that if you substitute epsilon and beta, that basically you are always in this region, as long as the number of local samples is larger than the number of machines, which is basically the case. And this is an interesting result. So there is no need to compute below the statistical precision. And if you don't do that, you can be faster than what you do if you look at the problem only from an optimization point of view. And by the way, note that we are not exchanging any Hessian here on the network. Okay. And how do we just quickly, I know I'm going with the time, just quickly over a quick comparison with the literature. I will make it short because I'm running out of time. And basically, if you look at the linearization, there were many, of course, many people did a great work. And before our paper, at the time, there were no works able to deal with the no smooth term and constraints, and these are pretty much the paper before our work. And then after, there's also a difference in terms of rate. We have a slightly better rate because our rate depends on the global condition number. The rate in the literature of local quantities are a bit worse than kappa G, but this is not very important. And then recently there are basically, after our paper was posted on archive, and during the revision, there were other papers appearing, in particular the paper of Sayed and the paper of Alex Goswetsky, I guess, I'm not sure about the pronunciation of the name. And but as you can see here, still dependent, the work of Sayed still depends on the local quantity, and the work of Alex instead has a global dependence on the global condition number, but cannot deal with the no smooth terms. In any case, the take-home message that all these schemes are basically we are using linearization, so they're not taking any advantage from the statistical similarity. There is only one paper concurrent to our work that used some the idea of, they try to basically, which is this paper that basically decentralized directly DANE, and introducing an algorithm called network DANE. They look at the problem from a different perspective, but if you cast into the umbrella of surrogate, it's a special case of Sonata corresponding to a specific choice of the surrogate. The scheme is applicable only to problems with a smooth objective. They cannot deal with constraints or directed graph. We also can deal with directed graph. And if you look at the rate, they can show an improvement on the rate thanks to the statistical similarity only in the quadratic case, which is roughly similar to what we have. They just lose a square term, but the rate is similar. If they work with non-quadratic non-quadratic loss function, the rate will degrade, and to what you have, there is no advantage from statistical similarity. Our result here holds for arbitrary functions of phi. We don't need to be quadratic. Okay, now that we have, I can skip this. Now that I think this is just to, so the take-home message of this first part is just to tell you that if you take advantage of the statistical property of the problem, you can speed up also the computation. Let's move now to the second part, which I think is my most recent work, where basically we look now at the high dimensional problem. And what I did is to left you with this result, these pictures, right? I left you with a lot of open questions, and basically we need to understand whether these results are an artifact of the simulation specific tuning, or if there is an underlying principle that we need to understand, we need to discover. And in particular, just to summarize, just to in case you don't remember or got lost, what we notice from the simulations is that these algorithms, despite of the theory, converge linearly up to a statistical error. And some algorithms, however, cannot be arbitrarily accurate and fast at the same time. Remember the speed accuracy dilemma. And the other big question is about scalability. There is this regime of interest where the statistical error is pretty much invariant, and we would like to keep the same convergence speed. And instead, some algorithms seems to work fine, others seems to slow down drastically. And so we need, in order to answer these questions, we need to bring statistical thinking in distributed optimization. And in order to do so, let's try to understand what is the underlying phenomena governing the statistical properties of the estimator here. And in particular, we go back to the lasso problem. And what we saw here is that basically the lasso error is well controlled, even if d divided by n is growing, as long as the number of samples scale, as long as I have enough samples. This will allow me to control this ratio and have statistically consistent estimate. So now the question is, this property holds even if the objective function of the lasso problem is not strongly convex in the standard sense, in the global sense. And why is that? The reason is that this vector statistical error, theta hat minus theta star, I will call this lasso error, is not an arbitrary vector that spanning the entire space. But under appropriate choice of the regularizer, this vector belongs to a very special low dimensional space set. And this set is what I would call the set of the sparse direction. In other words, this set is given, let's try to give you the intuition behind this set. This set is the set of all the direction. S is the support of the sparse vector theta star. So has dimension, let's say S, small s. And so what this set C is the set of all the directions such that the amount of mass outside the support is less than the amount of mass inside the support. So this is a sparse vector. And what's happening is that the vector theta, if you look at the picture, this is S and this is the complement, whatever is outside the support. So theta star belongs to S because it's exactly the support of theta star. Theta hat, we cannot expect that theta hat belongs to theta, has the same sparsity pattern of theta star, but it's still the solution of a lasso problem. So we expect some kind of sparsity in theta hat. And that's the reason why theta hat minus theta star may not exactly belong to S, but it's kind of close. It's definitely not a vector that is fully dimensional. And this is exactly what this cone does, telling me where this lasso error is. And thanks to that, we understand that we don't need, given that the vector, the lasso error stays in this cone of sparse directions, I don't need strongly convexity of my objective function everywhere. I only need strongly convexity basically in this cone. So I need strongly convexity only in some restricted direction. And this is what the lasso problem satisfies. The so-called restrictly strong convexity. And this is a general property that holds for several models, but in particular here I'm consider a simplified version where I assume that all the rows of X are IID, Gaussian with zero mean and covariance sigma. And what happens is that the curvature of my function, look, this is exactly the quadratic form built on the Hessian. is basically what? Satisfy this condition with high probability. What's the meaning of this condition? If you neglect this, if you neglect for a moment this term, this function, this condition here, all it is the standard definition of strong convexity for every delta. Now, what this condition is saying with this extra term is that, look, we are no longer, it's no longer true that the lasso function is strongly convex everywhere, but it's strongly convex only where this quantity here is strictly positive. And if you look carefully and you lower bound properly this quantity, you will see that actually this condition implies this, which is the standard, the so-called, which is exactly what I was telling you before, strongly convexity of the lasso over the cone of the sparse directions. And this is also known as restricted eigenvalue property condition, and it's weaker than the standard, the known RIP condition, restricted isometry property, for example. So now that we know, and by the way, remember, for our algorithm, we only need smoothness, right, to have a fast algorithm. And unfortunately, we notice that the gradient of the loss is not ellipses everywhere, but there is fortunately lasso problem satisfied a relaxation of the smoothness condition, and this is known as restricted smoothness condition. And then, as you can see, there is an extra tolerance term here on the standard definition of L smoothness. And now that we have this, we understand what are the underlying statistical property of my problem. The natural question is, can we take advantage of this statistical insight to design fast distributed algorithms? We know that in order to have fast convergence, we need to have linear rate, we need strongly convexity and L smoothness. And we know now that the function f is strongly convex and smooth in the cone C. So this naturally suggests a way to design our distributed algorithm. We want to design the algorithm in order to assure that the optimization error, if you want, the trajectory of my algorithm will stay inside the set C, so that the cone C, so that the algorithm will experience a roughly a strongly convex and smooth function. And this has been done in the centralized case. It works, and but the question is that how to make it work on a network. This is not a simple or trivial extension, and the reason is that we no longer have a master node or controlling the entire trajectory of the algorithm via tuning of the parameters of the problem and the algorithm. Agents do not have locally control of the entire trajectory. And even worse, we are using the network to average some information, which means that the network will introduce an extra perturbation, and this perturbation is topology dependent, and we don't know if and under which conditions the perturbation is controlled so that the trajectory will stay inside the set. All these are open questions. We don't know the behavior of any algorithm, existing distributed algorithm in the high-dimensional set. We start studying this problem, and we have an answer now for two algorithms: the Sonata algorithm that I introduced in the first vignette, and the DGD. I think that I don't know how much time I have. I will just try to focus on the Sonata, and basically let me try to summarize the main results. So what we have is that under few assumptions, assumptions on the model that we are using to generate the data, and of course the restricted strongly smoothness and convexity on top of an extra condition also requiring the restricted smoothness at the level of each function, and the proper tuning of the algorithm, what we can prove is that the estimation error of my algorithm will decrease at linear rate sigma, but we cannot reach any possible accuracy. This will decrease linearly up to a tolerance delta. Basically, you have linear convergence up to a ball around theta hat of the order of delta. And the rate sigma and the tolerance delta are function of a branch of parameter. The population parameter, the smallest and largest eigenvalue of the covariance matrix, the network connectivity, the number of agents M, and this ratio that controls the statistical consistency accuracy. And same story for delta, depends on a branch of parameters, including the statistical error here. Now, the question is that we have not done yet, because the question is, now we know that we will converge to some point theta infinity, and this point is within this ball delta. But remember, our ultimate goal is computing the theta star, the estimate, the unknown sparse parameter. So the question is that what are the statistical properties of this limit point? And what we can do, if you look at the closely, what's happening is that we know that theta infinity is within delta from theta hat. We also know that theta hat is basically delta stat away from theta star. This is what we know from here. So this will tell me that then if I just want to understand the statistical property of this theta infinity, basically, which is basically the mean square error, this average mean square error, if you just, it's simple triangular inequality, you will see that this error is bounded by what? By exactly the tolerance delta that I'm getting from my algorithm and the statistical error. Given that computing a point below the statistical precision delta stat makes no sense, what we understand from here is that all we need is that this delta is of a smaller order of delta stat. So the question is, when delta is a small order of the statistical error, and given the delta depends on these parameters, what we can do is that we need two conditions on top of the one that I mentioned before for convergence. I will go back to this condition in a minute, but what we have is that the average under these two conditions, we have that the average mean square error will basically converge string linearly basically the trajectory of my algorithm will converge to a point that converge linearly up to the statistical precision. Okay.
Aldo, yes. I'm sorry. I just want to remind you that it's around 8 o'clock.
Okay. So
7 o'clock.
Okay, can I maybe 2-3 minutes just to wrap up the?
Yeah, sure.
This? Okay, so let me just mention here quickly the main just one results that is I want to highlight here, that the conditions that we need to establish this convergence to the statistical precisions are one that is just the statistical consistency. This is the centralized result, and the results that we have also in the centralized case. So this is unavoidable, and then we need a condition on the network. The network has to be basically should scale like this. Now, this is maybe the cubic term is not very favorable, but it's also an artifact of our analysis. I would say that, but this condition on rho is unavoidable. We need a condition on the network because if you remember, we need to make sure that the trajectory stay within the statistical cone. And in fact, if you look numerically, if you do not impose any condition on rho, for example, this is an example where we generate a random graph, increasing the number of agents and keeping rho constant, you will see that the convergence will break, which is consistent with our theory that we need a condition. And I don't discuss how to, I will skip now the details. Or the one thing that I would like to mention, and with this I will conclude, is that remember that our interest is in this regime, in the regime where basically we can keep a constant statistical error. What happens to the rate in this case? We can prove that the rate is invariant. So basically, which is also confirmed by our simulations. This is an example where we increase the dimension of the problem, or we keep the number of samples growing according to the rule required for statistical consistency, and basically we converge to the same statistical error with linear rate that is almost invariant. And with this, I think that I can conclude. I mean, I hope that the take-home message of the talk is clear. I mean, on top of the details, the main message is that if you look at existing algorithms, I mean, in the high-dimensional setting in particular, many things are not clear. The existing theory does not work, and we need to bring more statistical thinking into the optimization in terms of analysis and also design. And sorry, I apologize if I took a bit too long. Sorry, I was not checking.
No worries, Aldo. Thank you very much. Thank you very much. Very nice talk. So we do have a couple of questions. First question, in your first case, just wonder if these arguments can be extended to stochastic optimization setting, meaning agents only do a mini batch of the data. That
so you're talking about the high dimensional setting?
The first setting,
in the first part of the talk where you
first part of the talk, yes.
Yeah.
This,
okay. So the first part of the talk, we didn't consider this case because I mean explicitly. So if you do mini batch, so this is mini batch. So you are doing like, for example, you want to do some form of variance reduction, or just using simple pure stochastic.
I would say pure SGD. I mean, that would be the most interesting case with pure SGD.
Yeah, we have not considered this explicitly. The thing is that if you think about that, I mean, if you play with the statistical, here we are you're using statistical similarity, right? So I don't know, we have not tried, so I'm just guessing. I'm thinking in real time. So if you look at the statistical similarity, basically the functions are similar of the order of the similarity of the function depends on the local sample size. So which means that in the moment that you do mini batch, you're introducing an extra error. And the problem is that it's not very clear as long as the error is, so you need to control carefully this error, because if this error is not within the below the threshold of the statistical similarity, this can put in jeopardy the entire convergence. In fact, I don't know if you notice the example, it's not the same thing, but if you notice the example in the convex case, you can reach fast rate, you don't put in jeopardy your rate, only if, for example, the statistical precision, the precision that you want is above the statistical similarity. When the functions, because think about that, we are taking advantage of the local function as a proxy for the entire Hessian. In the moment that this makes sense up to when the errors are not comparable with the difference of the similarity of the function, the Hessians, right? In the moment that you enter in a regime where the error is of the same order, then the Hessians will look different. So when you do if you don't work in mini batch, but you work with samples, and then you may have higher order, different errors that can make this similarity less useful. So I don't know. I didn't think about that, but in the high dimensional case, for me, it's more clear. In the high dimensional case, we need local restricted smoothness, which means that you need enough local sample size, which means that I'm not very clear how to make it work even employing some form of variance reductions and so on.
Yeah, because I'm also thinking about this along the line of this so-called linear speed up that they showed in this decentralized SGD paper. Yeah. So they also show that if you increase the size of the networks, there are improvements over the weight of convergence. I mean, let's say they look at strongly convex stochastic cost.
But they're using diminishing step size, right? To kill they are using diminishing step size, right?
Then, they need that. Yeah.
You need to have different time scales, I guess.
That's true. Yeah.
All right. Okay, great. So Yogo also had a question. The link communication overhead is with rounds. So how will there be any trade-off by compression, quantization, overall delay in information exchange?
Oh, here we are not. Yeah, here clearly we're. Sorry, go ahead. I don't know if I.
Yeah, and also how are the trade-offs affected by the underlying network topology? So those trade-offs.
Yeah, very good point. So in terms of in this work here, we didn't consider any form of compression or quantization. So we have an outcoming work we did some work on quantization, but here I don't know honestly how this will, together with statistical similarity, how the two things will combine together. We have not done that. In terms of asynchrony and other aspects, we have some works where we develop schemes that will preserve linear rate even where you are asynchronous, and both using either using linearization or general surrogate. But within the problem is sufficiently complicating, and also the system that, to be honest, we don't have a clear expression of the rate to be able to understand how it scales with the different parameters. We can only claim that you still have linear rate when you use tracking, which is not trivial because the tracking mechanism is very sensitive to error coming from delays and asynchrony. So this was one thing. There was another comment about what was the other, I think something related to this was the quantization. There was something else. The topology.
The topology, yeah.
Yeah, this is something that I didn't have time to discuss. Yes, the topology enters into this trade-off through, I'll try to make it short, through this condition. We need the scalability of the network like this. Now, this has two implications. In terms of design, this tells me that I need to design, if I can design the network, I need to design the network in a way that the scaling is like this. For example, in practice, we observe that m cube is more than what we need. In practice, 1 over square root of m is enough. For example, which means that you can use, it's here, you can use a random, this is an example of random geometric graph where the alpha degree grows with the m, with the number of agents, and then rho goes roughly like 1 over square root of m, and you still have the same linear rate up to the statistical. This is if you can design. If you cannot design, but you can only, you have a network, the network is given, you can try to enforce a condition like this with multiple rounds of communications. And if you do that, you need this round of communications. And the interesting thing here is that depending on the specific topology, you have different bounds from one. Note that rho depends on m as well. So this means that depending on the different graphs, 1 divided by 1 minus rho will change and will have different expression. I mean, this is related to the, what's called this? This is related basically to the heating time of the Markov chain, right? Having exactly the same weight matrix. And there are upper bounds for this. And for example, this can go from things like big O1 if you use some, I don't know, Erdős range graph to, or it can go to up to n or even n log n if you use a random geometric, or n cube, depending on, it can be as bad as n cube. So this tells you that depending on the different topologies can affect the, if you want to preserve the same statistical error and linear rate, you are paying more in terms of communications. But again, this seems to be unavoidable. The cube here does not make a big point because this will affect only logarithmically. The problem is exactly the presence of the network, because remember, you need to make sure that the trajectory stay within the cone of sparse direction, and this is affected by the network.
So basically, my understanding is that you need to make it a little bit closer to the centralized trajectory, like the one that you want to.
Yes, because this is exactly, you need a very good network, yes.
Right. Okay, great.
But the point is that we see that even numerically, if you don't have this condition, you break convergence at all. So it seems that some conditions on the network is unavoidable. It may not be 1 over m cube, because this can be an artifact of the proof, definitely. But some rho cannot be constant with respect to the number of agents.
Okay, great. Any other questions from the audience? I have one quick question. So in the first, I guess you already answered it. I just want to make sure. So for the first setting, if you have, for example, one node that's very big, like not very many samples, other nodes have very few samples, for example, does that work? Because that case is very unsymmetric, right?
Yeah, we didn't consider the case of.
So then the order will be like sample order will be different. So for the rest of the nodes, small nodes, the approximation will probably be bad, I guess.
Yes. Yeah, we didn't know. Maybe you need to account differently of this asymmetry. Another thing that we didn't consider is, for example, if the data are not from the same distribution, we only consider uniform.
Yeah, right. I see. Right.
Another limitation. I mean, I think that maybe moving to non-uniform data will be the step to understand how to, because here the idea is that basically we are cheating a bit because we are using this similarity to avoid to exchange Hessian information.
Right.
We need curvature, right, to go beyond gradient if you want to implement a form of mirror descent, but you don't want to exchange Hessian matrices. So that was basically, and then we are playing with this similarity, but yeah, I didn't consider the case, but if you just apply this, I think it would be unsatisfactory because I think you should consider the worst case, right? The case where,
right.
And this would be, I think that we should, in that case, we should do something smarter than just using this direction.
Yes. So yeah, that's the reason I said that you already answered, because you need the approximation to be accurate from local approximation to global.
Yes.
Yeah, right. Okay.
There's one in the chat.
Is there any question?
I mean, I can repeat this one here. So the question is about great talk. So the idea of restricted strong convexity and also RSM is very interesting. So is it possible to apply this idea to general objective functions? So like how to make sure that the optimal solution is covered by this RSM or RSC regions.
Okay, this is a good point, because I mean, yeah, there are basically the definition of restricted strongly convexity and strongly smoothness goes beyond, of course, lasso or quadratic function. Actually, there are other works of the group of Martin Wainwright and company where basically they extended this to fairly general model, going beyond basically quadratic, so there are different classes of M estimation problem, fairly general classes of M estimation problems where they satisfy some form of restricted strongly convex. And also you can deal also with the non-convex classes of non-convex functions and non-convex regularizers, as long as the regularizers are weakly convex. So you can cover SCAD, MCP, these kind of regularizers.
Mm-hmm. I think we are done with the questions.
Okay, great. So then let's thank Aldo. Thank you very much. This is a very nice talk, and yeah, so I learned a lot. So okay, so we'll stop here, right? Okay. So so thank you everyone for joining us today. Thank you for supporting our series, and next week we'll have another series, so please stay tuned. Okay, thank you again. Have a good night or have a good day.
Oh, yeah, by the way, the speaker next week will be Professor Anjali Nadic, and we will be continuing our journey with distributed optimizations.
Okay, great.
All right.
Okay, so we can stop.